We have a request for a roadmap from fall 19. And there it is. Where do we even start? Oh yeah, start here. Okay. You know, the most important reaction on the test is going to be the aldol, and the second most is the Claisen. And the giveaway for simple aldols is always looking like this. You start with an aldehyde or a ketone. You'll see one box that is after sodium hydroxide or some kind of hydroxide, could be KOH. And then the next box, same chemical, this time with heat. When you see that, and you will, I want the aldol reaction product in the first box and the aldol condensation in the second box. And I'm writing on stuff that's on the screen. My face is in the way. There you go. And when you look at the notes, there won't be this box in front of it. So yeah, how do you do these? Well, the aldol reaction, you copy the molecule. And on the alpha position, you draw a new bond to a second molecule that was identical to the first, except the carbonyl got attacked and it became an OH. All the other carbons are exactly the same. And let's just cut to the chase early on in this exercise and say, every time I see this group, which is like a 1-ethyl propyl group, I suspect we're going to be drawing it many, many, many times. So let's just do R. So we won't draw it any more times. Okay. How do you do the aldol condensation? You have to remove water from the aldol reaction product. Remember, the aldol condensation reaction involves first an aldol reaction and then a removal of water from the aldol reaction product. So beta OH loses, you lose beta OH, sorry, and you lose another alpha H. You get a pi bond where you had the new bond. Remember, the R group prefers being on the same side of the alkene as the carbonyl. That will be showing up on Monday. And we have the R up there, and we need the R downstairs. The bulkier R groups are away from each other. And that's that. And just for clarity, this is another way to draw the R group. So when you see that, it's just R. Didn't have to show that, but it is R. So what's new in this molecule? The R groups aren't new. The aldehyde's not new. The alpha and beta carbons aren't new. There's the R group. Oh, there's your nucleophile. This was a 1,4 addition on the aldol product. The nucleophile attacked there, and the electrons flowed from position 1, which is where it got attacked, all the way to the O. 1, 2, 3, 4. We call that a 1,4 addition, and the O minus is now resonating with an alkene. It's called an enolate. Enolates are the conjugate bases of aldehydes or ketones. And in this reaction, if you use a solvent that can protonate an enolate without protonating your nucleophile, here's your nucleophile. It's a C that goes to, it's a C that has an aldehyde on it and also a ketone. It looks terrible. I don't like it at all. Here's your enolate. Draw that first. It's got a carbonyl on top and a carbonyl down bottom. and a minus charge on the alpha position. And yeah, it's not even a plus sign because ethanol is the solvent. Yeah, that solvent's green. Normally, you can't have a C minus with a solvent that has protons. But this, remember, is the conjugate base of an acid with a pKa of, you guessed it, 10. It will not pick up a proton and go from 16 to 10. Ethanol's like 17, but really it's a little lower. So yeah, it's not gonna take the H off here. So yeah, sometimes you can have your nucleophile and a protic solvent. And yeah, then the alpha H that's here came from the solvent. The new bond came from a 1,4 addition. You don't have to write that on the test. Just helps you studying. And then what's going on here? I'm going to give you a heads up for Monday, so there's no big surprises. In some of the boxes, I'm putting the formula of the product. So you'll see a formula here. Okay. And you can check your work and see if you got the right number of C's and H's and O's. I don't know if it's helpful. We'll see on Monday. Okay. But what I love to do is follow these 1,4 additions with another aldol reaction. I'm just telling you, I love doing this. It's the best part of this whole test. And I do another aldol, in this case, condensation, because there's heat too, to make a ring. And this part at the end here is called, some dude put his name on it, or students of his had his name put on it posthumously, who knows. It's called a Robinson annulation, based on the word annular. Every year trees make rings, so you're making a ring. And I did give nice hint on this one. I did. I just noticed now. There's numbers. Robinson always makes ring size 6. You see numbers 1, 2, 3, 4, 5, 6? I do too. I don't think I gave that hint on the test. Maybe I'll retrofit it. It's not too late. Maybe I'll give you the numbers too. So you're going to make ring size 6 from the alpha carbon number 1. Although there's many alpha carbons, there's even alpha carbon 3, which has the most acidic proton. Can you tell me why? Alpha carbon here, that's a 10. Right? But it doesn't get you anywhere because you can't make ring size 4. That's what would happen if this C minus attacked the aldehyde. So you're going to make a lot of this anion. Acid base is always equilibrium, right? Back and forth. So you got to wait for the 1 in a million times when it doesn't take that H, but it takes this instead. Yeah, it is 1 in a million. pKa 10 versus pKa 20. Oh, it's 1 in 100 million or 1,000 million. I don't know. It's a lot different. But in chemistry, it doesn't matter. When it takes this H, it makes a product that makes a great ring size. A lot of talking here. Let's get back to business. So how do you follow the clues? Well, I'm just going to say the carbonyl looks like it has the same orientation there. And we'll go here. That was 2 connected. 2 connected to 1 and 6, 5, 4, 3. What's on 3 is an aldehyde that didn't get attacked. What's on 4 is our R group. What's on 5 is our R group as well. And the aldehyde got attacked. I'll give you the intermediate and then change it to the aldol condensation product. Don't copy this on 6. It's not going to be there after the heat. But there's your aldol reaction product right there. Makes an alcohol in the beta position. 1 is alpha, 6 here is beta. Heat gets rid of the OH, makes an alpha beta pi bond. And you might already know what I love doing with alpha beta pi bonds. You're probably going to be doing a 1,4 addition again. By the way, Robinson is no different than aldol. It just makes a ring. So makes the name even more silly. It's not even a new reaction. I see 2 different 1,4 additions. One's going to be from this nucleophile, and the other, oh, that's a carbon nucleophile. Well, more on that in a second, but this one over here is easy. You're going to need ethanol to provide the H. Product solvent ethanol is the most popular, and that's this H here, by the way. If you don't believe me, just try the mechanism. And the nucleophile, just copy the pink, except make it an anion. Copy the pink, but make it an anion at O2C minus. Yeah. You want to be picky, that's a CH. And then, oh, you can't, if you do this, you're in trouble. I mean, it's not big trouble. You can't do this. That's either a Grignard or an organolithium right there without its spectator. They don't do 1,4 addition because they're not stable anions. Remember, they also have to be a stable anion to do a 1,4 addition, not something with a pKb of -36, which is that. So you got to learn, if you haven't done so already, you're doing it now, the Gilman reactants add 1,4. Look in the textbook, chapter 19. It has a whole table of nucleophiles that are good for 1,4 addition, and it has a table of electrophiles that are good for 1,4 addition. This nucleophile is on the table of nucleophiles, and so is not this organolithium or Grignard, but a Gilman. And remember, those have copper in them and 2 identical R groups. 2 R groups. One of them gets delivered, and the other's just there for the ride. 1,4, 1,4. Love the 1,4. There are many videos on it. And then you're kind of in the bonus round when you get this far down the page. What's going on? Here's these funny R groups with another short form on them. It's R. It's not a new label, ladies and gentlemen. So these didn't change. These didn't change. Believe it or not, this carbonyl didn't change. It's this one up here. This was the aldehyde carbon right here. Can I put just a little green dot on? Just a highlighter, green highlighter. Why not? I use green highlighters ever. This carbon is that carbon, right? And what else happened here? Well, the nitrogen is this nitrogen. Yeah. So clearly not the right nitrogen for the job. Please remember this is an imine. Yeah. Imines come from what two species? Aldehyde already in the green dot, but nitrile, C-triple-N, not a nucleophile for making imines. The only nitrogen nucleophile that you ever learned to make an imine was a primary imine. Translation: nitrile needs to become primary amine. Question: how does one do such a thing? Answer: add hydrogens. What's that called? Reduction. C-triple-N is not a very polar bond, so one way to get there, when you're not having polar pi bonds, is our old friend H2PT. But I noticed something. That's not going to be step one. I noticed something. There's something missing in this molecule. This box is way too small. My apologies. The carboxylic ester is gone. Hey, it was beta to a nitrile. So step one here is going to be beta decarboxylation, which is really, it's the rap song. Do you remember that? To get rid of an ester that's beta to any, like a carbonyl or even a nitrile, apparently, you got to do the rap song. Saponification, chemicals, NaOH, AQ. Step two, this is going to get ugly. 2, HCl, and you also need heat. And that makes our blue 2 a 3. Our blue 2 is now a 3. And if you just throw a little DST action in there, which you don't have to, you never have to put DST in any boxes for me. Just a reminder that you'll make the imine condensation happen a little faster with a better yield. So you're going to make the amine with the H2 and PT, and it'll immediately attack the aldehyde because it's a nice distance away. It could have attacked the ketone, but I didn't show that. I bet there's another product. I didn't show it. And then DST just makes sure the water gets lost. So yeah, imines. And I just got to make sure you know that box is really now the yellow box. Groovy. What's going on in the next one? Wow. It looks like I hit the ketone with a nitrogen to make an enamine. So I hit the aldehyde. This was an aldehyde. This is the ketone. Ketone and aldehyde. Enamine times 2. And it looks like the nitrogens are connected. This one's a lot easier than it looks. Ethyl on N with an H. CH2 once, twice, dimethyl, CH2 once, N with an H, and an ethyl, comma, DST, because enamine formation is also this enhanced with the DST. And I believe that's all that happened. Enamine. And just carry on till the end of this box, the end of the stream here. H2PT. What's going to happen there? Kind of what happened with H2 and PT here. H2PT reduced the triple bond all the way to CH2NH2. Yeah. It'll do a C double N just as nicely, probably a little faster. What's the Grignard going to react with? There's no imine around. Carbonyl, though. Ethyl's going to attack carbonyl, get an O minus, HCl, put an OH on there. So let's try to draw this with this little, I think this actually will fit in the box. There's a first for everything. Could be famous last words, too. We got the big ring around the outside. N now has an H. Comes down to a C that has a new H. Sneak a cyclohexyl in here. I think I did that okay. Gonna have a new ethyl on there and an OH down here. And we got our R groups here. One there, one there. I think the OH can be in green, at least the O. There. Blue H. There's blue H. Nice. Mostly fit in the box. And then we have a new buddy here. H2PT is going to take these two alkenes down. And then our old friend NBS. NBS, when you see NBS, you think one of two things. Allylic or benzylic. Ding, ding, ding. Since we got rid of the double bonds that were alkenes, we're not going to have allylic. But we still have a lone phenyl group, which means the carbon attached to it is a benzylic carbon. Right here. Benzylic. Benzylic. Right there. So let's not mess around. I don't want to draw that beast, do you? New R time. Everything up to the benzylic, but not including the benzylic position. Oh, it was tricky. R prime. Oh, can't do it. Sorry, can't do it. R prime changed. Gosh. We'd reduced the double bonds in R prime. Oh, I'm so sad. So sad. Got to bite the bullet and draw it. Oh. Basic black here. So we're going to have an ET to an N, comes up to a CH2C, C, N with an ET, dimethyl, down, single bond, down, bond, 6 here. Not the next one, but the next one has benzylic with a F. And that's a F. Ooh, change color. Okay, and we got that. And I need my two original R groups. Original R group number 1. Original R group number 2. Yeah. Beautiful. Lithium and hexane reacts with organic bromides or chlorides to make Grignards. They make a Grignard. Grignards can be made into Gilmans, just like organolithians can be made into Gilmans using copper iodide. That's copper +1 iodide. And Gilmans love adding 1,4 to this thing here. It's got an alpha beta unsaturated pi. Nucleophiles coming in here. Gilman gonna do this. And I keep saying it, this first time I've written it this semester. 1, 2, 3. The electrons flowed from 1 to 4. 1,4 addition is how it got its name. We named the mechanism. Nothing to do with nomenclature. It's based only on electron flow. Okay, so I'm going to add that the whole deal up there. And this is the time to do R. This is the time. Everything up to, but not including the carbon with a BR on it. That's R prime. R prime, phenyl, new bond to the black stuff. Ding, 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 ding. And you're saying, wait, this mechanism won't give this. And you're right, this mechanism won't give this. This is only like one part of it. You're going to generate an enolate. Enolate, conjugate base of the aldehyde. There's ethanol present, pKa 17, 16 really. And the new H here from ethanol ends up there, 16 goes to 20. Okay, so the solvent provided a proton for that. And finally, the dead end of that. If you get down here, you're just doing awesome. If you get these right, you've got to pat yourself on the back. That's like incredible. 1, by this time, usually I found some kind of mistake on these things. And you couldn't get it because there was just an error involved on the way. That's okay, man. There's like 40 points on this page. 25 is what counts. And let's get some more of our 25 here. Start here. Start over. Now, when you guys see LDA, you got to think, oh, it grabs alpha H. Is that all? That's all LDA does? If you have a choice of different alpha H's, LDA likes the least hindered one. That's the 2 things you need to know about LDA. In this one, straightforward. There's only one set of alpha H's right here. This is a directed something reaction. If you're attacking an aldehyde in the next step, it's a directed aldol. If you're attacking a ketone in the next step, it's also a directed aldol. But if you're attacking an ester, which is what ethyl butanoate is, if you don't know that now, review nomenclature, then it's a directed Claisen. When you attack an ester, it's a directed Claisen. And what we're going to do is copy the blue again. Directed Claisens start off the same as directed aldols in terms of what you draw. Look. That's exactly the same as the aldol. New bond is to something about ethyl butanoate. I'm going to scribble ethyl butanoate right here. O2, C. First carbon of butanoate is the C. 1, 2, 3, 4. So we're going to attack the carbonyl. The pi will break, but because there's this OET on there, the electrons from the O minus come back and kick off the OET minus. And HCl provides this H right here after you're done. But the thing that happens with your ethyl butanoate, you keep the carbonyl portion. In the Claisen reaction, you keep the carbonyl portion and attach it to the alpha position. There you go. And later in the mechanism, the alpha H that was there after the attack, this alpha H gets removed because OET minus took it. So you have to put it back on with HCl. And there you go. That's beautiful. That's a dead end. Oh, we can do so many things with this now. I could, but I was out of room in my scheme here, so I had to stop. Because I can make this into a 1,4 nucleophile with that pK10 there. I love doing that. Don't worry. There's lots of opportunities still coming. Start here. Oh yeah, how do you make an alcohol from an aldehyde? Don't say oxidation. You'd be 100% wrong. You're reducing it. So you got three choices from what you know already. You could use H2PT and pressure, or you can use one of the hydrides, sodium borohydride followed by HCl, or lithium aluminum hydride followed by HCl. PBr3 to make the alkyl bromide. You're going to make an organolithium. Organolithiums will not add 1,4. They're going to add 1,2 to that same molecule. The nucleophile is going to attack the carbonyl like you learned in chapter 16. This is a very strong nucleophile, not stable in any way, shape, or form. That you didn't know that at the time it was called a 1,2 reaction. But the electrons hit atom number 1 and they flow to atom number 2. So the nucleophile is pictured to the left because right now it's got a C-. After step 1, it's got a C-. It's going to be the nu. Copy that in blue. Can I use my R? Does R take me? R takes me up to here. This one's an R. CH2 once, CH2 twice. New bond to an O-, which becomes OH with HCl. And has a vinyl over there. That's the 1,2 product. Oh, and then I threw it. Oh, wow. That's so. That is a blast from the past. That was mentioned in chapter 11. And I didn't throw this on your test. Just saying right now. It's another way to make epoxides. It works with allylic alcohols, which is what this is. So you're going to get an epoxide. There you go. And yeah, wow. Oh my goodness. What the heck's going on here? Ooh. It's almost time for numbers. We got the R. There's the R. 1, 2, 3, 4. R is attached to, we got the R. Attached to 1, 2, 3, 4. That doesn't work. I got that right, don't I? Have an extra carbon? Something's not right. So is it a dead end, I hope? It is a dead end. The fix is here. I have an extra carbon in my molecule. There might even be a fix on the answer key. I'm going to do a scribble out here. That carbon's gone. Reconnect here, recount. And we got 1, 2, 3. All right. Maybe I went the wrong way. I don't know what the fix is. And I don't want to get stalled on this. There's a mistake and I'm just going to cross it off. Oh, I didn't mind there. Stop there. Get rid of this last portion here. I don't like it. And I don't want to think my brain out to figure out how to fix it. You do not have anything like that on your test. Where are we here? Ah, good. 2 things going on here. Is there a clue there's 2 things going on? There certainly is. Can't do it in one step when there's 2 points. That's an ester. It has 3 bonds to O, the carbon here. This has 2 bonds to O. You have to oxidize it first. Get the right oxidation state. CrO3. That's a 3. Looks worse. 1. CrO3 H2SO4AQ. And then you want to make an ester. Fischer esterification is the best. DST if you, not DSN. If I erase it, everything gets erased. I'm just going to get rid of it. There. Okay. Didn't need it. Ester. Oh, LDA. Our buddy again. This time we're taking an H from the alpha position here with LDA, attacking an aldehyde. Oh, a directed aldol reaction. Directed aldol, DIR aldol. DIR stands for directed. And you're attacking propanal. I'm not even going to draw propanal. It's a 3-carbon aldehyde. We'll see it when we draw the product. R, doing the aldol products is always the same. Copy that, make the new bond. It attacked propanal. Propanal became O-. HCl picked up the proton. There's propanal, but I see the heat now. I see the heat. That's the aldol reaction product. What happens to an aldol reaction product after heating? Remove the water from the beta OH and the alpha H and make an alpha beta pi with the group pointing towards the carbonyl. Because this is less bulky than the R. And is that a dead end? It is. Dead end. Doesn't look it, but it is. This thing comes from here. Why is it 2 points? Same reason as before. Got to oxidize to a carboxylic acid first. 1. Same as above. And 2. How do you make an acid halide? Our friend SOCO2 and its colleague pyridine. What happens to acid halides in the presence of an amine? You get an amide. Amide, whether it's a primary amine or a secondary amine. And put some numbering on here. 1, 2, 3. Ethyl group is 4, 5, right? Comma 5. All right. So we keep all the carbons. 5 carbons. NN3 triad. 3 has an ethyl group on it, and then 4, 5 is the chain. Looks like we just got rid of the carbonyl. I shouldn't have said it that way. You didn't get rid of the carbonyl. You kept the carbon, you put 2 new H's on it. So don't think about the Hoffman rearrangement, which actually gets the carbon out of there. One, that only works with primary amides, so not a candidate here. 2, don't think about the Wolff-Kishner, which actually changes a C double bond to O into a CH2, which is what's happening here. But that only works with aldehydes and ketones. Don't give me the Wolff-Kishner chemicals. Don't give me the Clemenson chemicals. They do the same as the Wolff-Kishner. I need the reduction that takes an amide to an amine. That's what's happening. Look at the name. It says amine. Oh, he gave me the reaction that gives an ester becoming an aldehyde. The diisobutyl aluminum hydride. I bet it's on here later, but don't use that one. This one's just the reducing agent you would guess if you don't remember, because it does so many reductions. Lithium, aluminum hydride, followed by HCl always. LiAlH4, followed by HCl always. Okay. Going to the left, we have, that's a carboxylate. It's a nucleophile. Nucleophiles attack acid halides the same every time. The O- attacks the carbonyl carbon. You get an O- up here. It comes back and kicks off the excellent leaving group. And you will be left with, I'll draw the whole thing this time. Ethyl 1, ethyl 2, carbonyl, new group in black, O, it's even going to be symmetrical. CH2, C, ethyl, ethyl. That's how we make anhydrides. It's the only way to make anhydrides. Acid halides with carboxylates. That's the conjugate base of a carboxylic acid. And anhydrides react with nucleophiles pretty much the same as acid halides. NH3, good new. Just write new. Leaving group is already drawn for you here. Ethyl twice, CH, CH2, CO2 minus. What ends up attached to the other carbonyl is NH3, NH2, sorry. You don't get an ammonium. There you go. Primary amide. I'll tell you what I love doing with primary amides. Hoffman rearrangement. Yeah. Which is clearly the box to the right. Do you know how I know? The carbonyl is actually extracted from the molecule and you get what's drawn here. That involves bromine and base. Br2 and a lot of base. Remember the base was used in like 5 steps? Actually, no, yeah, 5, maybe 6. AQ, you can write excess if you want. You don't need to. That gives that. What happens here is the same as happened up here. We made an amine. Made an amine. How do you make an amine? And I kept all the carbons. Want me to verify? Ethyl number 1 attaches to C. Ethyl number 1 attaches to C. The C also has a second ethyl. Good. CH2. CH2. Yes. CH2. Oh, carbonyl became CH2. We did that up here. We did that right here. Yeah. The pentanamine. Here. You didn't see me draw it, so you weren't happy. You didn't see me draw it. You got two new H's on here. Right. Those are H's. Lithium aluminum hydride followed by HCl. So those are the two ways to get an amine from an amide. Reduce it, you get the same number of carbons. Do a Hoffman, you get one less carbon. Another thing that amines do, because they're the conjugate base of an acid with a pKa of 10, they're good nucleophiles and good leaving groups. When that's the case, you should be thinking about 1,4 addition. I told you 1,4 addition is one of my faves. I hope I've proved that by now. The new bonds to this position, and it's a nitrogen. It lost its H. I'm going to go CH2, CH2R, CH2, CH2, and our original baby blue R. Okay, wow. Dead end. No, not a dead end. What am I talking about? Ooh, ooh. There's my R. There's my NH. Here's my C. There's the next C. There's what used to be the carbonyl C. Highlighter. Yeah. Do I have that right? CH2 once, CH2 twice, third one's carbonyl once, twice. You got attacked by a nitrogen. Or did it? Did I count my carbons right? Here's a new piece. There it is. CH2 double bond CH. Carbonyl CH3. There's the nitrogen adding 1,4. And nitrogen adding 1,4. There's CH2, CH2. Third C has the two ethyls on it. Yeah. CH2, third C has the two ethyls. That's part of R. Might not have the right number of carbons, but it's an enamine. So enamines made from what? What two things are needed to make enamines? We learned them in chapter 16. Aldehyde or ketone, not provided here, with an amine, provided here. Okay? We got an amine, provided here. I just think this has one extra C over here. So, well, I can't erase here. This I can fix. Need white out. If I make the double, yeah. That used to be an aldehyde, a ketone. Double bond there. And if that was the question, now it makes sense that the attacker was right here. DST will help make the enamine. And my apologies, there was an extra carbon in the product. Yeah, we can make these roadmaps last all day, huh? Apparently. It's got everything on it. Oh, Now, how do I know this? There's clues that this is a normal old Claisen, simple Claisen. What's the giveaway? That's part of the giveaway. Claisens are always followed by HCl, but so are a lot of our reactions. So I don't want to use that as a definitive conclusion. But the fact is, we have the nucleophile, which is the base, actually, and it matches the leaving group on the ester. That's the clue for a simple Claisen. These matching. So if this happens to attack the carbonyl, which it will, you'd get an ester, but it's the same ester. That's why it has to be the same. I don't want a new ester. If this is attacking carbonyl instead of being a base, I want to regenerate the same ester. Then it's a base occasionally, and it grabs this H. And that's what I want. In fact, I'm going to grab that H and do a simple Claisen, which means I need this molecule copied again. And a new bond. It attacks a second version of the same molecule. It attacks the carbonyl. You keep the carbonyl because the electrons come back. And you get the CH2 that goes to C with two ethyls. I didn't use ours because I wanted you to see the simple Claisen. And the beauty of the products of Claisens is right here. What's the pKa there? Good guess. Except I suspect it wasn't a guess. He knew. But 10 is a very common number nowadays. This is why I say, whenever I use a 10, I'll just say, good guess or take a guess. A clue for you. And then you've made a nucleophile that can either add, that prefers adding one more if it can. And it seems to me I have this same molecule here that I had somewhere down there. I don't see it anymore. I'll just redraw it here. That's this molecule here. And it's a 1,4 candidate. So I'm going to go to R groups. R goes to CH2 carbonyl, goes to C with an R, goes to CO2 ET, and the new stuff there to the black, which keeps its carbonyl because there's more steps in this mechanism. One involves reaction with ethanol to pick up a proton on the alpha position. You want to see it? There it is. Ethanol provides that proton. Okay, so blue added to one side of the alkene and green to the other. Rap song. I see the combination of the rap song. Saponification, acidification, decarboxylation can be summarized with de-esterification. Oh, I like that. I just added that part to the rap song. The combination creates de-esterification. You put an H where that ester was. Copy everything except the ester. Saponification, acidification, decarboxylation creates de-esterification. There's going to be an H there. You don't have to show it, but there it is. Everything else is the same. All right. And then we got a choice of no less than 6 alpha H's. I will use my mouse to remind you there's 2 alpha H's there. There's 1 more down here. There's 2 more here. Oh, there's more than 6. 2, 3, 5, and 3 more over here. 8. LDA only knows how to take which ones? Least hindered, these. But that would be the result if LDA was the excess. You'd get an anion here and do something with that anion. Sorry? Say it again. Thermodynamic is what I want now, because equilibrium's allowed to happen. Equilibrium's allowed to happen when LDA is limiting, which means of all those alpha H's, now I want you to take the one that has the most stability of the enolate. And that would either be this one or this one. But if I go to this one, then I want to do some kind of reaction inside the molecule. And it won't make the right ring size. I can't, hey, if this attacks a carbonyl, it can't attack that carbonyl. It can resonate with it. But if it attacks that, what's the ring size? 1, 2, 3, 4. Don't make ring size 4 products using aldol reactions. We love ring size 6. If I use this one, which I can't because it's the limiting means if I'm choosing between this one and this one, which one makes a slightly better enolate, left or right? It's got an R group on it. Double bond there will be more stable. That's the one, and it makes a beautiful ring. You want me to count to 6 for you? I want to take this alpha H. 2, 3, 4, 5, 6. There's no heat. This will be an aldol reaction. I'll put the 1 here. I should have made a green ring. I'll make a blue ring. Numbers in green coming up. We got the 1 bonding to the 6. Did I get rid of all my numbers? Sorry. 1 had an R group on it. 3 had an R group on it. 4 had nothing, 5 had nothing, 6 had a carbonyl, which ends up being an OH. 6 also had a methyl. Do I have everything I need? On 1, there's an R, yeah. New bond right here if you want to keep track of new bonds. And there was a lot of clues. I mean, the next one kind of was a huge clue. I know it's rotated around a little bit, but it's not hard to see. Those are R groups. Oh, I forgot carbonyl didn't change on carbon 2. That's the whole reason this happened. There was a carbonyl on 2 and you made an anion on carbon 1. So let's do our numbers. 2's the carbonyl. Next door, 2, 3. Which one's 3? Which one? Well, you can make a double bond between 1 and 6. Oh, sorry. 2's carbonyl. 1's there, 6 is there. 5 has nothing, 4 has nothing. 3 has an R. Yay. Hey, we got rid of OH on carbon 6 and H on carbon 1. The 1. Terrible looking one. Tell me a way to do that. Tell me 2 ways if you can. It's going from an aldol reaction product. Aldol reaction. It's called a Robinson. It's an aldol to an aldol condensation. NaOH and heat, HCl and heat. Pick one, doesn't matter. Okay, and what's going on here? Oh, this is wild. Looks the same though. Hey, a nucleophile attacked carbonyl. A carbon nucleophile. Organolithium or a Grignard. Oh, I love it. One. Lithium attached to CH2, CH2O, attached to benzyl. Make sure you know there's carbons there, there, and there. Step 2, after every organolithium and after every Grignard is always what? HCl. I gotta put this H on here. Bonus. Oh boy, I don't want to even think about bonus. Oh, bonus is a reaction that was done 100 years ago called hydrogenolysis of benzylic ethers. You either know it or you don't, but I suspect you don't. Toluene is what phenyl CH3. They got a new H on the benzylic position. The alcohol got a new H. This one up here. You want to see the new H's? Here they are. Here they are. Not that one. This was fine. This there. Hydrogenolysis of benzylic ethers. Chapter 16. What's going on here? Oh yeah, we're getting our wrap on again. The only change was you lost the carboxylic ester. Sponification, acidification leads to decarboxylic esterification. But there's 2 points. Well, because there's 3 steps in that, or 2 steps if you want to be as concise as possible. Saponification, acidification, and in the same step, you can do the decarboxylation, just add the heat. Oh, yeah. Then we're in the true bonus round again. Why, if I want to do an aldol to make a new ring, is that the most important alpha H? These ones don't make a nice ring size. These don't make a nice ring size. 1, 2, 3, 4. These don't make a nice ring size. So these might make a nice ring size. Oh, 1, 2, 3, 4, 5, 6. They're both pretty good. Which one's going to make something that looks a little like this? Because that's my only clue. Up here's my only. This thing comes from some wild stuff. Yeah. The 2 H's that are potential for making nice rings, size 6. Let me count. 1, 2, 3, 4, 5, 6. Or 1, 2, 3, 4, 5, 6, attacking that carbonyl. Those are the 2. Which ones will lead to this? I believe. Let's see. There's the COO. That used to be a COO before it became an imine. And I think we keep that one and attack down here. Yeah. I think we're keeping this one. Look, this goes away, right? It's not in this ring anymore. So it got attacked. And the carbonyl here, it stayed carbonyl all the way and probably until this last step where you make it an imine from the carbonyl. So I'm liking this, just looking at this. So I want to take that H and do the aldol reaction product. And oh, what's the clue when you follow an aldol reaction with that? I could even be nicer, and I should be nicer, and say that when you do an aldol reaction and follow it with the same chemical and heat, you get an aldol condensation. I should have done that. Just to jog your memory. That's something you're supposed to look for. So I want the aldol reaction in this box here. Copy everything. And the next carbon also has an R. I'm going to put it in the middle though. And we made a new bond from not here, not there, carbonyl. Yeah. And we made a new bond here. Uh-oh, octet violation. What else happens in the aldol? You make the new bond and the C00 becomes a alcohol. There you go. And then the heat makes a double bond where you had this, the new red single bond. Yeah, the OH is gone. Double bond. And I got everything I need. Am I missing an R group? Looks like I'm missing an R group. Maybe not. CH2. Anyway. I'm not missing. I don't know what's going on. Oh, I do know what's going on. Look, there's the R group number 3. See, I'm confused. I see 3 R groups up here. And I see the 3rd R group coming on now in a Gilman. Gilmans do 1,4. We know that. Copy everything except for the pi bond there, the alkene pi. Yeah. And another R group here. Yeah. There's a small flaw on this, but it's not terrible. And it looks like above, except, you know, I found the mistake. There's an extra carbon there. There you go. You get it at the end of these things, yeah. And that imine from, that's an imine. Imine from a ketone is this, that's a primary amine. CHNH2. DSP. We're almost finished this. Take forever, these roadmaps. Hand is getting numb. What's going on here? Oh. Let's see. Looks like if I can make a cation here, this O can attack it. And that's just like HCl. Or how about H2SO4? That's better. I don't want a Cl on there. There you go. And I'm exhausted. Oh, we missed a box. We missed 2 boxes. Put off our exhaustion. Oh, we got excess. Now I'm only thinking about this one. I should have done these beside each other. Limiting wants to take this one, but that got us nowhere. So the next best one here. Excess just grabs the least hindered one, and that's the end of the story. It's called kinetic control. The first thing that can happen is the only thing that happens. The other one, can I use your last name? No, can I use it on the video? Yes or no? Yeah, Mr. Hamoud mentioned the thermodynamic control occurs when you have limiting LDA. This one's under kinetic control when we have excess LDA. You want to make ring, and I don't want to label everything all over again. I'll just add a letter A here. Once again, you don't need to label anything. It's an A and a 6, and A attacks carbon 2. Always ring size 6, guys. 2, 3, 4, 5. And where's 1? Well, 1 was on 2. 3 had another R. 4 had nothing. 5 had nothing. 6 stays carbonyl. A was the attacker. HCl and heat. Okay. Carbon 2 would be an alcohol without the heat. That'd be the aldol reaction product. With the heat, we lose the OH off the carbon 2 in this case, and we make a pi between A and 2. And this one was the aldol reaction as well. Oh, condensation, sorry. There's heat. Aldol condensation, no room. And this one was the thermal. No, backwards. Kinetic. And this one was thermal. Gave a more stable enolate. And yeah, we're done. And in that very long segment there, we have no time for more segments. We had a request for nomenclature, but I hope there's enough resources out there for you to do well on the nomenclature. There are. Pretty sure there's videos for it too. And adieu.